Hello, lovely humans. Jen Foxbot here. I'm so excited that this is our third episode of the Logistic Regression Machine Learning. Yay! So we continue our adventures in machine learning on our Math Mondays quest to understand mathematics. Woohoo! All right, so in this video, we are going to look at how to define the cost function for logistic regression. And since it's been a hot second, we're going to review what the cost function is. So we'll start with that, and we'll end with defining the cost function for logistic regression, or LR for short, because y'all know I like to be lazy. And then we will look at some plots, because yay, pictures. All right, so let's get into it. Remind me, what is the cost function? Great question, I have asked myself in a placeholder for audience questions. So the cost function, when we're doing machine learning, is a measure of the difference between our predicted value, the output of our machine learning program, and our actual value. So basically, how accurate is our prediction? We can use math to measure that via the cost function. Yay! Okay, so previously our cost function was defined like this, as a function of the parameters theta, which are parameters for our hypothesis function polynomial, and it is defined to be 1 over m, where m equals the number of training examples. Basically, how much data do we have that we're using to train our machine learning model. And it is the sum over all of this data, kind of like, and we're going to take a 1/2 multiplication factor, like a fancy average kind of thing. And we basically just subtract each of the, we subtract the difference between the actual value and the predicted value. So for each of the data points, and then we square it. Again, fancy average. So actual value, predicted value, how off is our predicted value, and then do this for every single data point. So this is really important because we're not just looking at one data point, right? We want to make sure that our machine learning algorithm is accurate for our entire training set. Very important. Okay, that's cool, easy peasy. And then the goal is to minimize the cost function. So for example, if we were to plot the cost function for a linear regression, we would ideally get a plot like this, where we would minimize the cost function. We plot j of theta, number of iterations, number of its, woo, okay. And so that would be the cost function that you're like, yeah, that's great. And that would give you some information about your parameter values. That tells you what parameters are best for our hypothesis function. Okay, so that doesn't really work for logistic regression because our hypothesis function is all funky and it's nonlinear. So for funsies, our hypothesis function for LR, we'll say LR, and hopefully that's not too small for y'all. Hard for me to see on my screen, but logistic regression hypothesis or predicted function of x equals 1 over 1 plus e to the negative theta transpose times x. All right, so we need to define a cost function that works with this shenanigans. So, new cost function. Yay. Okay. So our new cost function, which is going to be a function of our hypothesis function, h of x, and it's going to depend on our actual values, y, and it's going to have 2 parts. So the first part is if y equals 1, we're going to use a negative logarithmic function of our hypothesis function, like so. And this is if y equals 1. And if y equals 0, which is the other option in our binary logistic regression exploration. We're going to have a negative logarithmic function of 1 minus our hypothesis function. Here, it looks like a q, that's supposed to be a theta. And we will see why in a second with pictures. Yay, pictures. I know we're doing math, but like pictures and math are critical. At least I think so. Cool. Okay, so yes. Okay. So again, to recap with logistic regression, we are really looking at data that's either 1 or 0, on or off, frog or toad, habitable planet, not habitable planet. And so we need a way to reflect that in our cost function and basically make sure that when we are getting predicted values, that our predicted values are matching the training set. So I'm going to use colors because yay, colors. So let's first plot the case for y equals 1. So if y equals 1, let's make this a little bigger, longer. Okay, so our cost function is going to go on the vertical axis, and our hypothesis function is going to go on the horizontal axis. And a negative logistic function looks like this. Woo, boop. And the point at which it kind of reaches the horizontal axis is 1. Cool. So this gives us some data, or I should say some properties that we can point out. Okay, so props. Okay, properties. So number 1, well, how should I say this? Yeah, okay, when y equals 1 and h and our hypothesis function equals 1, then j equals 0. Woo! That's awesome! Because if we look at this plot, we're like, okay, for y equals 1, if our hypothesis or our predicted value is 1, then there's no difference between our predicted and our actual value, and the cost function is 0. Yeah, what's up? That's what we want, right? The other thing that we want is if our predicted value is way off of the actual value, we want to make sure that we penalize that so that we're not going to get a machine learning algorithm that's like, excuse me, this planet is definitely habitable when it's not. Future humans will be very happy that we made sure that that was not an outcome of our machine learning function. So in that case, for when the case of y equals 1 and h and our predicted value is 0, that's the worst case possible because it is going to give us the exact opposite of what we want. Then j, our cost function, goes to infinity. That's a really smushed infinity symbol. Let me draw that better. Okay, which is what we want. Cool. Okay, so yay for negative logarithmic functions, helping us deal with binary data sets and nonlinear data sets. Okay, let's look at the other case. So second plot. Woo, here we go. Okay, so for this one, for this case, we are looking at situations where y equals 0. And again, same type of plot. We have the cost function on the vertical axis and our hypothesis function on the horizontal axis. But in this case, our cost function is going to look like this. Wow, yeah, okay. So we have this asymptote here, and this point is 1. So again, 2 key pieces of information or properties. Props. Woo. Okay. So number 1, if y equals 0 and our hypothesis or our prediction is 0, then we want our cost function to be 0 because yay, our predicted value was accurate. So then j is 0. Cool. And if we look on our plot, if y is 0 and h and our hypothesis function is 0, then boom, our cost function is 0. Look at that. Yeah, 0. Yay. Okay. And the second situation is if y equals 0 and our predicted value is the exact opposite, which would be 1. Exactly. So if our hypothesis function is 1, we're like, ooh, that's really bad. We don't want that. Then our cost function is going to go to infinity. And so we look, okay, if h theta, if our hypothesis function is 1, then the value of j goes, whoa, off the page. Not enough space on my chalkboard or page to draw that. It goes to infinity. Woohoo! Okay, so that's what we want. So this cost function will help us to figure out what parameters, hey, bringing it back to parameters, work best for our hypothesis function, or the function that we are going to use to make predictions on new and unknown data. Yay! So all of this hard work up front with machine learning helps us to make predictions much, much, much easier in the future, or with data that we can't really label. Cool. Okay, so that's how we do cost functions for logistic regression. Yes. All right. Please let me know if you have any questions about the topics that we covered in this video. The logistic regression cost function, like what is the cost function, or the sigmoid function. And we are going to continue our exploration of logistic regression machine learning. Yay! So let me know if you have other types of questions about LR. Awesome. All right. So thank you very much for watching, and we'll see you next time, friends. Bye.